This lesson deals with a complex power example. You can find these notes in the ECE202 ebook in chapter 16, starting on page 6. Suppose I have a two-terminal element, and I apply 440 volts RMS across its terminals. Suppose that I measure the apparent power drawn by this box, and it turns out to be 3 kilovolt amperes. And then I can measure the power factor and found that it was lagging in a value of 0.9. Could you solve for the magnitude of the current in RMS, the value of P, the value of Q, and Z sub L, the two-terminal element impedance? Could you also draw the power triangle for the load? All right, we know the magnitude of the apparent power was 3 kilovolt amperes. Of course, that's equal to VRMS times IRMS, and since I know V, I can then solve for I. So 3K divided by 440, 6.818 amps, but again, this is RMS. Our real power, or average power, is VRMS times IRMS times the cosine of theta. And I know that the value of cosine of theta was equal to 0.9. 440 times 6.818 times 0.9, get 2.7. It's going to be kilowatts. So the reactive power is VRMS times IRMS times the sine of theta. So I know the voltage and know the current, but theta now is the inverse cosine of our power factor, which was 0.9, but it was a lagging power factor, so there's a minus sign with a leading and a plus sign with a lagging. So we'll have a plus sign here. Notice our angle is positive. The inverse cosine of 0.9 is 25.84, and so the sine of that times the voltage and the current is 1.31 K, and our units are volt amperes reactive, so VARs. Since I know the angle and I know the voltage and the current, I can calculate the impedance. So it's 440 divided by 6.818, and the angle was 25.84. So that gives me an impedance, the magnitude and angle, and I can put that in rectangular form by taking the cosine of this times this, and then taking the sine times this. I get 58.08 plus J 28.13, and again the units would be ohms. We can actually solve for the reactive part, given the results we just found. So at 60 hertz, the value here is omega times some L equivalent of the load. 28.13 would equal 2 pi times 60 times the inductance. So 28.13 divided by 2 pi 60 would be an equivalent of 74.6 millihenries. Of course, the real part here is the resistance equivalent circuit, or equivalent value called R sub L, at 58.08. So we can draw the power triangle. I had a length of 3 kilovolt amperes, and I had an angle of 25.84. So I can draw that with a protractor. The projection here would be 2.7 kilowatts. We'd solve for that. That was our P, and then our value of Q was 1.31 kilovars, and then put a J there for the imaginary part. This is an example of using our formulas for complex power.